Hi, I'm Steve Mosier, a solutions architect with Cisco Systems, and today I would like to demo for you a very high throughput, highly available, and secure solution for inter-region and region to enterprise site connectivity with the Azure cloud. Okay, so first let me pull up a few slides I put together. Okay, so this is a Transit VNet, a highly scalable, highly available Transit VNet. All right, so this is an overview. All right, so this is very secure. It encrypts traffic. It encrypts traffic between Azure regions and between Azure regions and enterprise sites. So it's IPsec encrypted, and it uses DMVPN technology, which, by the way, I'm going to rewrite this for SD-WAN very soon. It's high bandwidth. The routers that are encrypting the traffic, de-encrypting the traffic, and in making intelligent decisions, they can scale out. You can increase the number, and then you can contract the number if you need to. It's highly available. There's many different fault tolerance mechanisms, and I'll go over that in a few slides. And it supports agility. So the application owners creating VNets and deploying their applications, they want access to the enterprise network. So the way this works is through tagging. So the transit VNets are tagged, and the candidate participant VNets, say the application owner's VNets, they're tagged as well. And if they're tagged with the same thing, then the Polar program will build the automated peering and install routes and things like that. So it's very easy. So from an application owner standpoint, I can speak with enterprise IT, and they can give me the proper key value pair to tag my VNet with, and then within the Polar cycle, via a minute or 10 seconds, I'm going to have connectivity to the correct enterprise network. Okay, this is very secure, and this slide illustrates it uses DMVPN between all the different sites. For instance, if you have this deployed for the same cluster, and what I mean by cluster is you could have multiple transit VNets that support development in different regions, like one per region. And I could have production transit VNets for production traffic. And if I tag my application VNets with dev or production or whatever my enterprise segmentation naming standards are, the Polar will create the correct VNet peerings so that the traffic connects to the right enterprise network. So it's segmented correctly. Okay, so it's secure. Here we see different VNets or Azure regions communicating with each other over dynamic VPNs, and in fact, there are some enterprise sites as well. It's high bandwidth. So as we see at the top of the diagram, there's an enterprise site, and the enterprise site could be using a DMVPN to communicate with this regional VNet as well. And you could have as many routers as you want, 2 minimum for high availability. But then here we see 5. So the capacity of this would be 5 times the IPsec performance of the instance sizes with the operating system that's running on here. So it's high bandwidth because, well, not by default, but most routing protocols use equal cost multipathing. So the enterprise site has 5 different equal cost paths to get down to the VNets that are at the bottom of the slide. And in this solution, we're using BGP, so we enabled the iBGP multipathing. And it's quite a bit. You can go up to 32, so the upper bounds would be 32 different routers. Okay, and then from the Azure VNets, the peered VNets, they point to their default route, their traffic, to a VIP of that standard load balancer. And then the load balancer does the load balancing. So that's very, very high bandwidth. It's highly available. From the enterprise to the sites, you're using a routing protocol, BGP, for fault detection, peers down and that sort of thing. But then from the load balancer up to the routers, we're using health probes. So that's great if a router is down. But what if a router was just deployed and the BGP peering hasn't come up yet, right? So it would be up. It might even actually work with the health probes, but you don't want the load balancer to black hole the traffic. So what I did is wrote a script that runs on each router that says, if I'm not BGP peered with my route reflector, then I'm going to shut down my gig 2 interface. So if you use the deployment script for the demo.py file, it'll deploy the routers, and at first their gig 2s are shut down. The script will be loaded, the BGP configurations will come up, and then when the router is finally up and peered, then it will bring up the gig 2 interface. So it won't even be a part of the pool until it's eligible for traffic. So it's highly available. And as I said before, it's agile, with the idea being that these VNets are tagged. If a VNet is a transit VNet, it'll have a tag that says it's a transit VNet. It'll have a key, the program key, and it'll have a cluster name. And that's how the Polar program knows what clusters are being offered within a region. Then, as I said before, an application owner or whoever owned the VNet that needed to connect to the network would have received the proper key and value from Enterprise IT and goes ahead and configures that on the VNet, and then the Polar program automatically configures the bidirectional peering and the user-defined route within that participant VNet to point as a default to that load balancer's VIP. So this scales quite a bit as well due to the limit for VNet peering being 500 peers. So that's quite a bit. So I've shown DMVPN with one DMVPN cloud, but here's an example with two. So here's a DMVPN for all inter-region Azure VNet traffic on the right-hand side. And then there's a second DMVPN cloud for region to enterprise access, and that could be over an express route. And what's great about this is now your inter-region traffic's encrypted, and your region to enterprise site over the express route is encrypted. And once again, it's scalable and it's highly available. All right, so here's a demo that I'm going to show you. Okay, I deployed a hub site, which is kind of like an enterprise site. It's got DMVPN to my transit VNet, where I have 2 routers deployed right now. I didn't see a reason to deploy 5. And I have 2 application VNets called VNet 1 and VNet 2. Now the transit VNet has these following tags. So Auto TVPC Cluster Manager and Dev. So I'm simulating like a Dev cluster. It's true for the TVPC SILB. So this is how the program's going to know that it actually has a SILB and it's a router and a way out to the enterprise. And I went ahead and tagged it with the IP address of the standard load balancer. So it makes it a lot easier when I need to go find what that address is from the transit VNet. So then what we're going to do is we're going to tag these different VNets, and we're going to watch the Polar program build the peering and install the routes. So let me go ahead and hop over to Azure. So I used a demo script that I put on GitHub that you could use to deploy the transit VNets and all these other ones if you want to see it all work together. And this is what we have. We have the 4 different VNets. Here's the hub, the transit VNet, and then the 2 application VNets. And I can take a look at my transit VNet, look at the tags. The tags are there. The program did that for me. And then here's my first application VNet. See, there are no tags. And we see there are no tags on the second VNet as well. So what I'm going to do is I'm going to go into the application VNets. Okay, there's one application VNet. I think this is the other one. Okay, So I've got the application VNets, and the way I configured these is there's an internal VRF that ends up going to a table that would then go across a peering connection if it was there. So that's pretty simple. That way I can have a global table for my SSH to access these things, and then just use the internal to simulate being on the network. Then I could show the, this is the hub, I believe. Okay, so this is the hub. Oh, slow down a little bit. And if I show run, you can see the configurations on the hub. It's the DMVPN hub. And I added multiple internal VRF IP addresses so that I have something to ping. And what it's going to do is it's also the route reflector. Any of the routers that come up, they're going to be a part of this peer group, and they're going to be clients, and they're going to receive a default route from this hub. That's the way that I can go ahead and ping these addresses from anything that connects to it. So there's my hub. Let's just see how DMVPN is doing. Oh. All right, we see we have 2 spokes off of the hub. These are the global addresses. These are the tunnel addresses. So I'm going to log into these routers as well. Okay. Okay. And over here. Okay, and I'm going to show that I'm receiving that default route. Yep, from the enterprise. And we've got that. So obviously we have a BGP peering and adjacency there. So okay, and we see that I have, so both of them are up. BGP is up, and their gigabit 2 interfaces are up for both of them. Let's see, maybe I didn't show that. Okay, so the SILB should be running just fine right now. So what I'm going to do is go back and show IP. I'm just going to ping one of these addresses from these application VNets. All right, and it's not going to work because they're not connected to the network yet. That's 1,000,000, that should do it. Okay, so now for this VNet here, I want to connect to the network. So what I would have done is spoken with enterprise, the IT folks, and they would have given me the key value pair that I would tag onto my VNet right here. And the enterprise folks would be running this script, this Polar script, and it runs in a loop. All right, so right now I have it set to 60 seconds, which I'm not going to wait for, in GitHub. So now it's going to be a 10-second loop. And this 10-second loop is going to go through, and it's going to grab everything, all the VNets. So this is using the Azure SDK to grab them all. And I'm going to run through, and I'm going to find anything that has this TVPC program key as the key value in the VNet. And this is set under, so I imported this module, the config module, and I said, hey, this is where I set this. So when I deployed the transit VNet, I used that key, and then I said dev. And now all of my other VNets that are participating that want to connect to this transit VNet, they need this key and then that dev value that I deployed with my transit VNet. So that's what I'm going to do now. Oh, wait a minute. Before I do that, I'm going to go ahead and start this puller, and it's on a 10-second loop. So let's just go to the terminal. And what I'm going to do is for the Azure SDK, I need my subscription ID and client ID for my API, for my app, and these other values here. So what I did was wrote a shell script so I can go ahead and set those as environment variables. I'm going to do that now. And then when I run my puller program, it'll just pull those variables and I don't have to put it on the screen. So it's running now. Okay, here we go. I have I'm just printing the counter there every 10 seconds. And I'm going to go ahead and configure that tag. So I'm in app VNet 1. I'm going to go ahead and set a tag. That's going to be dev. I'm going to save that. And looks like we've got another 6 seconds. Okay, so it's identifying the transit VNet for the cluster. Then it finds the VNet with the appropriate key, with the appropriate cluster that doesn't have a peer, and it built a peer. So now, if I go back here, I can go to my peering, and I see here it is. So this side has been built, and then if I go to my transit VNet, that side has been built. And then let's take a look at the private route table for that VNet. And what we're going to see with routes is now we have the default route that goes to, this is the VIP for the load balancer. So I'm also going to show, this is the other VNet, and there's no route here, and that's not the easiest way to find it. We'll also see under peerings, there's no peering. All right, so I'm going to go ahead and change this other VNet too. So I'm going to go to the overview, change the tag, and put the appropriate values for this transit VNet in here, and save it. And it shouldn't be long. Let's hit refresh a few times. Oh, there it is. Boom. Caught it right near the end of the wait period. And it's updating. Okay, here we are. Both are there. Both are connected. So now what we see is the first VNet is actually up and the pings are working. The second one isn't pinging yet because it takes it a little bit. It takes just a little bit to spin that up in the background. Oh, great. That thing already died on me. Oh, look at that one too. All right, well, we are going to go ahead and just go back in here. Oh, you know, let me blow that up a little bit. This username is in that config file as well. That's where you set it. It can be anything you want, but it has to pass like a check. Like it can't be admin, or the CSR will reject that. All right, so here we are back in this one. Nice if I didn't have to do that again. Okay, we're going to go into the other router that's being load balanced too as well. Oh, good. Go through with that. Up. Okay. So I'm going to put on a terminal monitor and show run interface G2. I've turned on NetFlow for ingress on the interfaces that the load balancer balances to. So what I'm going to do is take a look at the net flow. I named it FM1. And what we can see is first, these are the health probes. So I just have it's SSH. This IP is Azure's address for services. So that has to be reachable through that internal network. And what we see here is we've got 10.102.4.21.1. This is the ping for the second application VNet. So let's see, and that's it. So if we look at this one, show flow monitor FM1 cache. Oh, we see here's the first one. So that's just what it picked, was 10, or the balancer sent traffic to both of those for the different pings that are being sent right now. So what I want to show is the fault tolerance. So obviously, if a router's down, BGP goes down. Or if an interface goes down, like my DM-VPN tunnel interface, what I want to do is show that the load balancer will transfer traffic over once the health probe fails. So if I shut down my DM-VPN interface, BGP is going to die. It's going to time out. Okay, and see, so my interface is down. So you see the traffic it's unreachable. The router says, hey, I can't get you there. So what needs to happen is the load balancer needs to stop sending traffic to the router. So what's going to happen, I can't remember if I did a terminal monitor on here. Well, I guess I didn't, because now the ping is working. And what that means is that the health probes failed. So I can still see that in the logs. And what we'll see is the EEM script found that BGP is down, and then it went in and it shut down the gig 2 interface. So I can do a show IP interface brief, and we can see that gig 2 is down. And traffic is switched over. So if I look at the NetFlow logs over here, we've got, I think that was the one right there. Yeah, it was. So it was the 10.100.1.4 to 1.1.1. Yep, and it's transferred over. Obviously it is because it's working. And there's the other one. So now, what I'm going to do is I'm going to bring that interface back up again. And we'll see that the BGP adjacency will come up, and because the adjacency just came up, then the internal script running is going to bring up that gig 2 interface. So okay, so here it goes. I think I'm going to hop over to the hub router, take a look at that too. And of course, that's not going to work. Timed out. So I'm going to go ahead over here. It's 52.160.199.83. And I'm going to put a username in front of that. And SSH to the hub router again. All right, so what we have Oh, I didn't bring up the tunnel yet. No shut. Okay. All right, so now we're going to run this test right now. So tunnel 1 should be coming up now. Three 6. I think that's what it was. Oh, well, here we go. All right, so tunnel 1 came up. The BGP neighbor came up. The script identified it came up, and it brought up gigabit 2. So this should be, yep, DMVPN is up. Show IP, BGP, VPN v4, all summary. Obviously, BGP is up. I'm receiving routes. And what is interesting is that before, this source and this source, these were, both were over here. But now, if I show flow monitor FM1 cache, and I'm just going to include 10.100. All of those. Here's the source, here's the 1.4. It moved the 1.4 back from here over to here. So that's really nice. Okay, so now everything is working as it's supposed to. We have traffic flowing. We can see that the peering is built through the polar. And I guess the one thing that I haven't shown is failover. So let me go back here and just remove a tag. So let me go to an application VNet. And let's just say that now we don't want to connect this anymore, or we want to connect to something different. We could just type a different value in here. What will happen is this will be removed from the cluster. So now, at the end of this polar cycle, its wait period, it's going to identify that the transit VNet has peering with another VNet that doesn't have the labels. So this goes through and it cleans it up. It breaks down both sides of the peering and it removes the UDR. And there it is. The peering is removed. So if I look at peerings, peering's gone. If I look at the transit VNet peerings, that other peering was gone. And the UDR is gone as well. Let's see if I can find it. It's the private table. Yep, it's gone now. So it's cleaned up. Then if I want to clean everything out, I could go ahead and change the tag. Let's say I wanted to deploy new routers in a new availability set, but we're servicing the same cluster. What I could do is go into my transit VNet, and I could go to the tags, and I could just delete that. Now the program is going to go through and find every peered VNet and pull the tags out of it. So let's see, I just saved that. So we should see at least the VNet 2. Hope I didn't miss it. Being removed. Well, let's see. Oh, what did I just do? Oh, I didn't save it. Okay, here we go. That's why it didn't take effect. All right, now we can just look at the peerings. Just going to refresh this. Okay, deleting. There it goes. So that would be a way that you could, I don't know, for instance, change router software or make some other changes. you could easily cut over. You don't have to go through and rename all the tags of the VNets that want the service. You could deploy a new cluster, remove the tag from the old Transit VNet, put that tag on the new one, and then this thing's just going to build all of your peering and everything again that quick. Really, it's fast. So that's it. So these things are all removed out of here. Well, it will be. It doesn't take long. And if I look at VNet 2, it deleted both sides, and the UDRs are gone. So that's everything. So this is that's what I wanted to share. So I believe that this is the highest throughput, most highly available, and secure method for building an encrypted overlay network to protect Azure region to region and Azure region to enterprise site traffic. If you have any questions, I'd love to hear from you. And I'm going to go ahead and post a link to the GitHub repository with this video. And here's the repository right here. There's a few useful things. So there's a accept terms to accept the software terms. There's the demo where you can deploy either just the transit VNet, or you could deploy like the whole thing that I just did. And there's the Polar script that is really useful. So thanks for spending your time and watching this video. I hope you enjoyed it. Have a great week.